Welcome, everyone, to this explainer on Chapter 14, Big Data and NoSQL. We're going to dive right in today because, honestly, this is where modern software engineering gets incredibly interesting. For decades, traditional relational databases have been the absolute gold standard for storing information. Nice, neat tables, rows, columns. But in our modern world, those traditional systems begin to seriously struggle when data becomes just too massive, when it arrives incredibly fast, or when it comes in completely weird, unstructured formats. So today, we're going to learn exactly how the industry tackles these massive data problems. Here is our structured program for today's lecture. 1. Introduction to Big Data. 2. Scaling up versus scaling out. 3. The Hadoop framework. 4. NoSQL Databases. And we'll wrap it all up with 5. Summary and key takeaways.
All right, let's kick things off with Section 1, Introduction to Big Data.
So you might be wondering, what exactly makes data big? It isn't just about having a whole lot of files. It's actually defined by 3 specific characteristics, which we call the 3 V's. First up, we have volume. This is the sheer quantity of data we're talking about. We are no longer talking about gigabytes here. We're talking about petabytes of data being generated by global e-commerce and social media platforms. Second is velocity. This refers to the speed at which data enters the system and needs to be processed. Think of continuous streaming data like RFID sensors in a massive warehouse tracking thousands of items all at once, or high-frequency stock market ticks. Finally, variety. This refers to variations in the structure of the data. As I mentioned, traditional databases absolutely love structured data, those neat rows and columns. But big data is often completely unstructured. We're talking tweets, videos, emails, the whole shebang. When you combine massive volume, high velocity, and complex variety, well, traditional relational databases simply fail.
Just to put that volume into perspective, we all know what megabytes and gigabytes are, right? But in the realm of big data, companies like eBay are dealing with clickstream data that easily reaches into dozens of petabytes. And some enterprise data warehouses are operating at the petabyte and even exabyte levels. That is just a staggering amount of information. So, as a quick micro recap for you, big data is defined by volume, velocity, and variety, the 3 V's that push traditional databases way past their breaking point.
Moving right along to Section 2, Scaling Up versus Scaling Out.
When an organization runs out of storage, they basically have 2 choices. The first is scaling up. This means you keep the exact same basic architecture, but you migrate to a single, larger, more powerful, and frankly, vastly more expensive system. Think of it like trying to transport more goods by buying one absolutely massive, highly engineered, super expensive lorry. The problem there is that there's a physical and financial limit to how big one lorry can get. Big data instead relies on scaling out. This means distributing your data storage across a cluster of thousands of low-cost, regular commodity servers. To go back to our analogy, instead of buying one massive lorry, you buy a fleet of thousands of cheap standard delivery vans to share the workload. It is highly cost-effective and, for all intents and purposes, practically limitless.
Now for Section 3, the Hadoop framework.
Okay, before we dive into this one, we really need to bust a very common misconception. Please recognize and remember this for your exams. Hadoop is not a database. There is no Hadoop database management system. Rather, Hadoop is a Java-based open-source framework. Think of it as the engine that powers those scale-out architectures we just talked about. It's the underlying platform that distributes the data and the processing across those thousands of cheap computers. And it consists of 2 main parts that work brilliantly together: HDFS for storage and MapReduce for processing.
Let's define that first part. HDFS, or the Hadoop Distributed File System. This is how Hadoop actually stores files. It assumes your files are going to be absolutely massive, so it splits these massive files into physical blocks. Now, your standard database block might be, say, 8 kilobytes, but HDFS defaults to a massive 64 megabytes per block. It takes these blocks and copies them, or replicates them, across thousands of different computers. This is what provides fault tolerance. If one of those cheap servers suddenly dies, the system doesn't crash because a copy of that exact same data block already exists on another server. Within HDFS, we categorize the computers into 3 specific types of nodes. First up is the name node. You can think of this as the brain or the directory. It doesn't actually store the files themselves. It stores the metadata, which is the information about where all the pieces of the files are kept. Second, we have the data nodes. These are your thousands of workers that hold the actual replicated 64 megabyte data blocks. Finally, the client node.
This is simply the interface that connects the user's application to the HDFS when you want to request file reads or writes.
Now for the second half of Hadoop, MapReduce. This is the processing engine. Here's the thing. If you have petabytes of data distributed all over thousands of nodes, you literally cannot pull all that data over a network to a central computer to process it. The network would instantly clog up and fail. MapReduce solves this with a truly revolutionary concept. Instead of sending the massive data to the processing program, it sends the processing program directly to the data. It divides the job into two phases. The map function sorts and filters the local data into key-value pairs. Then, the reduce function collects and summarizes those local results into a single final answer. Let's look at how this MapReduce process flows step by step so you can picture it. First, the client submits a processing job to a central program called the job tracker. Second, that job tracker talks to the name node to find exactly which data nodes hold the relevant data blocks. Third, the job tracker contacts programs called task trackers that are sitting directly on those specific data nodes. And fourth, those task trackers spin up mappers and reducers to process the data right there, locally. It's a really perfect strategy to divide and conquer without crushing your network bandwidth. Here is a great note directly from your textbook regarding this process. Because these nodes are built on commodity hardware, best practices suggest keeping mappers on a given node to 100 or less. You really want to minimize resource strain and prevent the node from crashing. So, just a quick micro recap for you. Hadoop is the framework that allows you to scale out. HDFS handles the distributed storage, and MapReduce handles the distributed processing by actually sending the program to the data. All right, let's jump into Section 4, NoSQL Databases. We define NoSQL, which stands for not only SQL, as a totally new generation of database management systems. Traditional relational databases use those rigid tables and strict rules, which we know as ACID properties, to guarantee that every single transaction is perfect. But when you are dealing with big data, those strict rules slow everything down to a crawl. NoSQL intentionally throws away those rigid tables and strict ACID rules. Why? To achieve massive speed, scalability, and high availability across distributed networks. Now, the NoSQL model is basically a broad umbrella containing 4 main categories, and each one was developed to solve very specific big data problems. We generally categorize them into these 4 main types: key-value databases, document databases, column-oriented databases, and graph databases. Let's quickly break down how each distinct behavior works. First, we have key-value databases. These are conceptually the absolute simplest and fastest. Data is stored as a simple key, like an identifier, and a value, which is the data itself, grouped into what we call buckets. The database doesn't care at all what the value is. It could be text, it could be an image, literally anything. It just blindly stores and retrieves it incredibly quickly. Contrasting this, we have document databases, like the very popular MongoDB. They also use keys, but the value is always a tag-encoded document, usually in a format like JSON. Because the database actually understands these internal JSON tags, it allows software engineers to perform highly sophisticated queries. This makes document databases absolutely fantastic for modern web applications. Next up are column-oriented databases. Instead of storing data row by row like a traditional database, they store data grouped by column families. This design is for lightning-fast aggregation and analysis over impossibly huge data sets. Finally, we have graph databases, such as Neo4j. Now, these don't look like tables at all. They use nodes, which are like entities, and edges, which define the relationships between them. They are specifically designed to map complex, highly interconnected networks. Think of mapping out billions of Facebook friends or LinkedIn connections. So a quick 10-second micro recap. NoSQL dumps the strict relational model for speed. You use key value for raw speed, document for web apps, column-oriented for massive analytics, and graph for social networks. And finally, Section 5, Summary and Key Takeaways. Now, after hearing all this, you might be sitting there thinking, relational databases are completely dead. Actually, scratch that. An important note from the textbook points out that they absolutely are not. Relational databases remain vital. For day-to-day transactions, like billing systems where every single penny must be accounted for accurately, you absolutely for sure still need the strict ACID compliance of a traditional SQL database. And this leads us to a vital modern design concept, polyglot persistence. It's a fancy term, but it just means the coexistence of a variety of data storage technologies within a single organization's infrastructure. Today, a successful enterprise doesn't just pick one database and stick with it. They use relational databases for their billing, document databases like MongoDB to run their website content, and the Hadoop framework for mining massive logs of user behavior. It is all about using the right tool for the specific job.
Let's recap the most important facts you really need to recognize and memorize for your upcoming tests. 1. Big data is defined by the 3 V's: volume, velocity, and variety. 2. To handle big data, we scale out using clusters of cheap commodity servers rather than scaling up. 3. Hadoop is the framework that makes this possible, combining HDFS for storage and MapReduce for processing. And remember, say it with me, it is a framework, not a database. 4. At the database layer, NoSQL abandons strict relational tables and ACID rules to achieve massive speed and scale across those distributed nodes. And 5. Modern systems architecture relies on Polyglot Persistence, combining relational and NoSQL tools seamlessly.
And that brings us to the end of our explainer. I want to leave you with this final, provocative thought. As you move into your next software engineering module, and eventually into your careers as developers, how will you implement Polyglot Persistence? When you are faced with a new system design, how will you evaluate the behavior of the data to choose exactly the right database tool for the job? Something to think about. Thank you for learning with me today, and I wish you the absolute best of luck with your studies.